Welcome, everybody. It's my pleasure today to introduce Žiga Virk, and he'll be telling us about information encoded in persistence diagrams.
All right. Thank you, Henry, again, for the introduction and for organizing this workshop. Of course, thanks to the other organizers and for organizing this seminar as well. So I'll be talking about information encoded in persistence diagrams. So this is going to be like a survey talk going through a variety of results that explain how features in persistence diagrams actually appear. So we will not really dive into technical details. We'll mostly just state the result and kind of try to outline geometric intuition behind the result. And of course, at any point, feel free to stop me and ask a question. All right, so here's our setting. This is the standard TDA pipeline. We will start with either with a metric space or simplicial complex. We'll mostly be focusing on RIPS filtrations, on open RIPS filtrations, but except for the last result where we will actually just have a sublevel filtration. And then, of course, given a filtration, we produce a barcode or a persistence diagram. And the question is, of course, what does it mean? What does actually generate all these points? Is there some sort of secret meaning in this diagram that we don't see or something like that? So I'll be using a terminology of a footprint. So footprint will mean that like an effect on a persistence diagram that is induced kind of by a geometric or a different property of our space. So I'll be talking about different footprints in persistent homology that are induced by certain features of the space. So to start slowly, we'll start with a classical footprint, so to speak. That's a topological footprint. So of course, when people started constructing check complexes and earth complexes, the first idea was to reconstruct a space up to homotopy, at least, and model it in some way. Talking about RIPS complexes, the first result in this sense came with Hausmann, that was like 1995, who proved that if you have a close connected compact manifold without boundary, then for small r's, the RIPS complex there is actually homotopy equivalent to your space. Now, this result has been generalized, extended in various settings. So it turns out that a result like this holds in persistent setting, meaning that for small r's, those inclusions of RIPS complexes are actually homotopy equivalences. And let's see how this works on a specific example. So this picture that just appeared is actually a geometric representation of many of the footprints we'll be talking about today. And the main goal of the talk is essentially to explain this picture. So what we have here is a torus. It's not a standard torus. It has some deformations. And on the bottom, we have part of persistence diagram of a RIPS obtained through RIPS complex built upon this torus. So through consecutive slides, we will explain more and more of these barcodes. And we'll explain this part like maybe 5 minutes. So what topological footprints tells us at this stage is that if you take small r, of course, we just detect the homology of a torus. We get one component, we get two holes, and we get one two-dimensional hole. So this is all pretty standard stuff. There are many generalizations by Lacho and others where various results with discretizations are proved, but all of them actually go along the same lines. I mean, the result is the same, but the proof techniques are sometimes different. Right. So for small r's, at least for nice spaces, we know precisely what we get. And then increasing the scale beyond small scales, the easiest thing to consider is a one-dimensional homology. So at this point, we'll focus on one-dimensional persistent homology of geodesic spaces. And it turns out that it actually describes shortest homology basis. So let's see what the theorem states. So if X is geodesic, geodesic means that whenever you have 2 points in a space, so X and Y, there exists a path in your space between these 2 points of length, the distance between X and Y. So all distances are essentially realizable by a path. So in such a case, if you have a shortest homology basis, which is finite, so this is something that happens if you have semi-locally simply connected spaces. So in practice, well, oftentimes, almost all the times in TDA, then the one-dimensional barcode actually consists of intervals from 0 to 1/3 of the lengths of these generators. So each bar corresponds to one generator. They're all born at 0, and their death times actually tell you what's the third of the length of that generator. So let's take a look at an example. So if you have a nice torus here, here we have 2 shortest homology bases. So the bar corresponding to this one, the red bar, it terminates at 1/3 of the length of the geodesic A, and similarly for the other one. And if you approximate, if you want to compute this thing by a computer, so if you do construct some sort of approximation of a torus, and you approximate the geodesic metric, compute persistent homology, and take the critical simplex that will kind of terminate this bar, the critical simplex here will actually be a triangle going around here. So the critical simplices actually tell you where those geodesics are. And similarly for this one, the critical simplex here will just go around here. And you can use them to specifically locate your geodesics. Right. So let's see how this works on our example. We marked 3 geodesics, A, B, and C. Now the blue geodesics, A and B, represent the shortest homology basis, and their death times are 1/3 of the length of the corresponding bar here, and the same for this one. So that's it. Now this story can be expanded actually in a paper where this proof is given. The entire machinery is done for persistent fundamental group. So I think in Link's talk, we saw persistent homotopy groups and things like that. So just one interesting note, in differential geometry, one important feature of a space is a systole. So that's the shortest non-contractible loop. And the same theorem, as is stated here for homology, actually holds for fundamental group as well. So you start for small r's, the Rips complex, the fundamental group of the Rips complex of a, let's say, manifold is isomorphic to the fundamental group of the manifold. And as you're increasing R, you're actually just chopping off loops by their lengths. And the first time something happens, well, that's the first time you have a non-contractible loop, and that's a systole. So essentially, if you computed persistent fundamental group, the first critical scale would just give you 1/3 of the length of the systole. And just like here, in this case, you could actually locate that systole just from the critical simplex that gives you that thing. Right. So much about one-dimensional persistence. And then, of course, we're interested in going to higher dimensions. So here we kind of had geodesics generating one-dimensional homology. That's kind of natural because you expect dimensions to be kind of respected. But then going beyond that, we can also construct a combinatorial footprint. So the idea here is that actually internal combinatorics of the Rips complex generates some interesting homotopy types. And by far the most prominent example of this is the theorem of Michal and Henry. So they prove that if you take S1, they use geodesic metric, but essentially could also use Euclidean metric. We'll just reparameterize things. And see, you can actually determine the homotopy types of Rips complexes. So for small r's, we actually get the topological footprint. So we just reconstruct S1. But then at 1/3, the homotopy type jumps to 3-sphere. So that's kind of hard and easy to see. On one hand, I mean, at 1/3, you start getting these triangles. And essentially, you get a cycle's worth of triangles. So if you take a circle and span kind of not triangles, but disks around, you kind of feel the 3-sphere. Now, this is how you can try to imagine it. There's no proof of this result this way. The proofs are mostly combinatorial and more involved. But the point is that combinatorics here gives you something non-trivial. So I like to call this thing like a Hopf effect in persistent homology. So one-dimensional geometry induces higher dimensional homological features. And the result actually is that at the beginning you get one-dimensional sphere, then three-dimensional sphere, then five-dimensional sphere, and you get all odd-dimensional spheres until you reach 2/3, which is the diameter of the circle, if the circumference is 1. Where no, at 1/2, at 1/2 it should be right. Yeah.
Yeah,
Something
your scales are slightly off, but it's fine.
2/5, right?
Yeah.
Yeah. Sorry. Yeah. Right. So there are two questions, of course, arising from this. Well, can we prove a similar result for any other simple space? I don't know, sphere, torus, or anything else, or just metric graph, which is not just a circle? And that's a very open question. There are some results. So for example, Henderson has some results where we can say something for some sorts of ellipses of small eccentricity for the first scale where you pass the topological footprint. And there are similar results for regular polygons, but in general, those all use kind of circular structure. So if anyone needs a challenge here, yeah, I mean, determine homotopy types of Rips complexes of spheres. So people would be interested in that. And then the second question that actually leads to a footprint is, all right, so suppose you have a subspace, simple subspace, let's say closed geodesic, which is isometric embed, which is a geodesic S1 embedded into your space. So can you see this evolved combinatorial homotopy types in the whole space as well? And it turns out that often you can, and that's what we call combinatorial footprint. So that the combinatorics of a subspace of a Rips complex induces the same, let's say, homology elements in persistent homology of your space. So how do we prove that such a combinatorial footprint exists? There are two criteria. The first one, well, two different criteria. They're both sufficient. The first one is kind of a global condition. So if you have a space and you have a one Lipschitz retraction onto your subspace A, so I call such a map contraction, meaning, so it's a retraction and the distances shouldn't increase. They can stay the same or they can decrease. Then the persistence diagram of A actually embeds into persistence diagram of X. Now, in a way, this is kind of a tricky wording. If persistent homology as a persistence module embeds into another persistent module, what you get is that bars kind of embed into bars, but they can be prolonged at the beginning. So what I'm saying here is a stronger statement. I'm saying that with those embeddings, the lengths of bar remain the same. So this is more than just an injection of persistence modules. And this is something we can see here. So on our torus, we can have, of course, there are two contractions that are kind of natural. One is onto A, and the other one is onto B. And say, if you take this one, our result will state that, well, you have a one-dimensional bar, and then you have a three-dimensional bar going to length, twice length of A divided by 5. So maybe I don't want to mess things up here. And then we'll get a five-dimensional bar and so on. So the entire combinatorial picture of a one-dimensional circle appears there. And the same holds for B, essentially. So this explains this new bar. So existence of these retractions is actually interesting. So in this specific case, we have two retractions. In general, if you have a metric graph, there always exists a contraction onto the shortest loop. But if you take other loops in metric graphs, there may not be contractions, even if a loop is a member of shortest homology basis. So it's kind of, at the moment, it's not really known how easy it is to get these things. But in any way, an existence of such contractions would be interesting. For example, a map like this actually gives you one Lipschitz cohomology element in first dimensional cohomology. And because it's one Lipschitz, it's actually perfect representative for circular coordinates. So there are papers that are using circular coordinates. And well, I mean, if you want to have a stable circular coordinates as possible, well, you might be interested in such maps. And whenever you have such maps onto a circle, of course, I mean, existence of such maps can be maybe kind of guessed from certain patterns in persistence diagram. All right, so that's one way to get a combinatorial footprint. It's a global condition because you need to map entire space somewhere. There's also a local condition. So technically it's written down here, but maybe I just want to show a picture. If you have, we'll just state it for a loop. If you have a isometric embedding of a geodesic S1, and it kind of has a hyperbolically shaped neighborhood. So essentially it just needs to be geodesically convex for some sufficiently large scale. Then persistence diagram of alpha, sorry, in dimensions from 3 on actually embeds as well. So you don't get a one-dimensional thing. That one's been classified through one-dimensional footprint, but you get all higher dimensional spheres. So what would such a result explain? So if you take this circle, this one kind of has, let's say, sufficiently large geodesically convex neighborhood. Yeah, maybe I don't know how to draw it nicely. And our theorem here states that, well, it will generate a three-dimensional bar starting at 1/3 of the length of it, because it's a footprint of this combinatorics. And then again, you'll get 5-dimensional bar, 7-dimensional bar, and so on. So this is a local condition. You don't need to consider the entire space. As long as you have nice neighborhood, you know that this is a combinatorial pattern that appears in your persistence diagram. And yeah, so this condition is something actually that naturally appears in hyperbolic surfaces. And I suspect it also appears in hyperbolic spaces, but we haven't gone through that proof yet. We only prove it for hyperbolic surfaces up to now. Right. So much for combinatorial footprint. The next footprint will be a geometric footprint. So in combinatorial footprint, we kind of wanted to embed persistent homology of a subspace into persistent homology of the entire space. Now, geometric footprint is a bit different. It will tell you that certain embeddings of, let's say, geodesic circles again, generate some new homology elements. So here's a statement. If you have a, of course, yeah, let's say a geodesic circle, which is locally short as geodesic, and again, with wide enough geodesically convex neighborhood, and if it is not a member of shortest homology basis, so what does that mean? That means that it doesn't have any one-dimensional footprint. It means you cannot detect it with one-dimensional homology. Then the theorem states that you can actually detect it with two-dimensional homology. So that's funny. Let's take a look at the picture here. So suppose this is my alpha and it's, let's say, homotopic to beta, which is shorter. Well, at length alpha divided by 3, what do we get in Rips complexes? I mean, of course, we get this entire surface of the cylinder between two geodesics. We get kind of a triangle here, which can be represented as a lid. We can fill in this part as well. And the same here. So you can imagine we get a two-dimensional homology generator like this. So we have two lids, and then in between, we just triangulate this surface really slowly. I mean, with small triangles and everything works out. So how can we see something like this on our example? So C would be such a circle. And so at C divided by 3, you would put a triangle here, and there's already been a triangle here like a lid. And this part of the surface would actually form this two-dimensional homology class. Now, the birth time of such a class is well defined just by this picture. It's not really clear when such a bar would terminate. We only have a bound for its death time. So x1 would be smaller or equal to the length of gamma. And gamma in this case is the kind of the longest curve, at least if alpha and beta are homotopic. Gamma is kind of the longest you have to stretch a curve going from one to the other. And I think this is closely related to Arienstock, which will be later today. I think she's talking about having homotopies between paths. How much do we have to stretch that thing? Well, that stretching, maximal stretching, gives you the upper bound for the death time here. Right, so that's a lot of theory. Let's take a look at one small example. So what did we do here? So we took 400 points on the sphere. Well, yeah, actually, maybe we took 400 points on the sphere. We cut off the top parts, approximated geodesic metric, and computed persistent homology with ripser.jl. So that's just a Julia version of ripser. And we kind of get what we expected. So let's try to interpret these things. So down here, we get one-dimensional bars. And if you play with your sample a little bit, these bars will become smaller. So essentially, this is kind of noise that comes from discretization. If you take a better sample, this will decrease. And then our results tell us that, well, here we have a geodesic circle. Now, it's not a shortest homology base because the space is it's actually contractible. But still, by combinatorial footprint, we should be getting 3- and 5-dimensional homology bars here. But it turns out that, from that result of Michal and Henry, those bars are really short. And this one actually is a 3-dimensional bar. You cannot see it, but I zoomed in and checked in. So this is actually of dimension 3. It's very short, but I mean, that's as short as we expect it to be given the result. A bar that is more prominent is this 2-dimensional bar. So this is a geometric footprint of this circle. So the circle is not a member of shortest homology bases, but it has large enough, I mean, it's not hyperbolic neighborhood, but it's still it's a neighborhood that satisfies our conditions so that we can push it onto a circle and not increase the distances. And it actually gives us this long bar. And a funny thing, again, of course, if you take a simplex that generates this 2-dimensional bar, well, it's going to come around here. I mean, one of these, depending on your sample, of course. So our footprint actually also gives us a way to detect these geodesics. Take a critical simplex and that's where things are. Right. So that explains almost the entire picture there. So we have 2 more footprints, 2 more ways to induce parts of persistent homology, which are a bit different. Yeah. Now, one of them is cheating again, just like topological footprint is cheating. I will call a footprint arising from stability result a footprint of proximity. So stability result for persistent homology tells you that, I mean, one of the versions tells you that if 2 spaces are close in Gromov-Hausdorff distance, then their persistent homologies, well, the diagrams are fairly close as well. So I won't go into details. I'll just show you how such a footprint can be used, or put it differently, how a stability result of this sort can be used in the spirit of footprints. So if you recall Hausmann's result, that was the first topological footprint for Rips complexes, essentially. So in that paper, he actually conjectured that the connectivity of Rips complexes is a monotone function in R. And that's something that up until recently has been supported by all known examples and computations.
And that conjecture was probably for manifolds.
Yes, for manifolds. Yes. Yeah. Of, let's say, yeah, closed, connected manifolds without boundary. Yeah, sorry, forgot to say that. Of course, the wilder the space is, the more you can do. And it turns out that this conjecture doesn't hold, so I'll just outline in 3 lines that prove, which uses this sort of footprint of proximity, so to speak. So the idea is the following. By results of Ferrier and Okun, you can take 3 sphere and kind of deform it. So we're talking about Riemannian manifolds, and deform it so that it gets arbitrarily close to a 2-sphere. And then you just use the footprints as before. So 2-dimensional sphere has a persistent homology that looks something like this. It starts just with a 2-dimensional bar. That's a topological footprint. Y is a 3-sphere, so it starts with a 3-dimensional bar. So that's, again, topological footprint. But because it's very close to S2, a 2-dimensional bar also has to appear somewhere. So that's your counterexample. I mean, you have to polish up the details a little bit, but that's the gist of it. This part is given by topological footprint, and this part is given by footprint of proximity. And here's your counterexample. All right. And the last footprint is called the footprint of rigidity. So that's, I think we just put an archive paper on, well, preprint on this on last week or maybe this week. So what does it talk about? So talking about stability, persistent homology is stable, as long as we're talking about bars and diagrams. But critical simplices are not, right? So that's, I mean, essentially they cannot be, because if you have a discrete setting, if you have a filtration of a finite simplicial complex, well, you know, there are no non-constant continuous functions there. So let's see how does, what I mean by this non-stability. If I deformed my torus so that I thickened this part a little bit and made this part a bit thinner, then C would become a part of the shortest homology basis. And then this endpoint would kind of correspond to C, not to A anymore. So the critical simplex would jump from here to here. Now the result, this footprint that we're going to state is not going to be for RIPS complexes, but it's actually just going to be for sub-level filtration, so finite simplicial complexes. So let's see how that works here as well. So here are 2 filtrations of a finite simplicial complex. And let's say we're interested in homology class A minus B. So essentially, when do components of A and B join? So what's given here are 2 filtrations. They are at distance epsilon, or this is 2 epsilon. On the first one, the green edge is the one that connects the both components. So this is the critical simplex terminating one 0-dimensional bar. In the second filtration, this is the critical simplex. So it kind of changes. And the result that I'm going to state in the next slide essentially states that if critical simplex can change for some epsilon perturbation of your filtration function, then 2 things can happen. And one of those things is actually that here you can see you get a higher dimensional homology class. Right, and the other thing is something we will see later. All right, so let's rephrase this. So this is the last non-trivial slide. Let's put it this way. I will reformulate our result in a setting of persistence barcodes just so that I can state this picture. So here's our setting. You take a finite simplicial complex. You take an injective filtration function. That means that each simplex either kills something or gives a birth to something. And suppose you have a, let's call it a prominent bar in n-dimensional homology. So this is a prominent bar. What does it mean? It means that for some epsilon, no other bar passes through these two lines in dimension n. You can have bars like this in dimension n+1 or other dimensions, but at least for this dimension, this is the only bar. This is actually a condition that tells you that the bar with which you pair this bar generated by alpha is unique. All right, and then the theorem tells you whether the critical simplex terminating this bar is rigid, meaning constant for epsilon perturbations. So a simplex terminating a bar like this is of dimension n+1. So, in a neighborhood, you have a bunch of simplices of dimension n+1. All simplices terminating these bars are of dimension n+1, and also all simplices giving birth to these bars are of dimension n+1. So essentially, epsilon perturbations in this picture can change the order of n+1 dimensional simplices considerably. But what the theorem states is that if you have no birth here, in this green part, so this is the first condition, and no deaths here, then your critical simplex terminating this bar is rigid. And that's nice because it tells you that, okay, even if I perturb my filtration function, the critical simplex terminating it will be rigid. And that's important if you're interested in locating representatives of this bar. So representatives of bar are usually obtained from the death simplices. So either you just draw a death simplex or you extract the entire homology representative for it. And knowing that that simplex is kind of rigid, that it doesn't move around simplicial complex is nice. So I think that the nice thing about this result is that you can deduce rigidity of a terminal simplex without going through filtrations, without looking at what actually persistent homology is, just from bars. And that's it. I think I'm 4 minutes over the time. Yeah, so maybe I should just skip to the last slides slowly. There are other footprints as well that I didn't have time to talk about. Henry and Boris have some really nice geometric footprints, essentially. They don't call it footprints, but I would call them in the context of this story. In this paper, they connected filling radius with the death time of the fundamental class of a manifold. So that actually gives you the death time of a two-dimensional bar in our major torus example. So that clears that enough. And there are other papers, for example, talking how curvature can be detected and so on. So that's it from my side. You're welcome to ask questions now, or if you feel like you know about a result that would fit into this context or a story, you're more than welcome to share it at this point as well. So that's all from me. Thanks.
All right, let's unmute and briefly applaud for Žiga. So we have some time for questions. Questions from folks?
I have one. Okay, Žiga, thanks for the talk. And can I see the page where about the two-dimensional barcode, the theoretical result?
Mm-hmm.
Yes, I think that. And can I see the inequality for x1 again? Yes. So here, the x1 is upper bounded by length of gamma over 3.
Mhm.
And in this picture, right in this slide, to make this equality holds, x1 is equal to length of gamma over 3, then it would be enough if the length of beta is equal to length of gamma in this picture. Am I correct?
If length of beta was equal
If the length of beta is equal to
you mean
length
here?
of, yeah, then x1 will be exactly equal to length of gamma over 3.
Oh, you mean that the death time would be exactly length of gamma?
Yeah.
Not really. So if you wanted to fill this representative continuously, then yeah, you would have to go through gamma over 3. But Rips complexes are kind of discrete. So, I mean, I haven't checked this, but I imagine that, you know, you can get just before gamma somehow with some triangle, and then have a tetrahedron kind of jumping over to another triangle. And both of them would be kind of a bit shorter than gamma.
Okay. And do you know any example making this equality holds?
Yeah, I mean, if you have, let's say, this is alpha, and it goes up a little bit, and then it's kind of flat here, and then it goes down to beta, right? So in this case, you would actually have to get across, and wiggling left and right a little bit is not going to help you. I hope I answered your question.
Yeah, thank you.
Yeah. So there's an example where this is a strict bound, but in general, if you have something smooth, I think you get something smaller.
More questions?
Yeah, there's something in chat, but I cannot open it. If there are any
Oh,
questions.
no. Yeah, I sort of, there were some small questions in chat that I tried to address.
Thanks.
So I'll ask one sort of motivated by your lovely last slide of the literature of all of these footprints. Aside from the theoretical results, have you seen applications of this? Like, where have these footprints been used on real data sets, if at all, yet?
Not really yet. I mean, topological footprint, I mean, this is kind of reconstruction. So I guess this has been used around, but not the others, really. I mean, I know Tamal Day has some geometric algorithms to compute some of one-dimensional persistence, and I think I've seen some other papers, but I'm not sure I've seen anything like on real-world data, like in biology or something else. And this is all fairly recent as well. So no, at this point, I don't think I can point to something very scientifically applied, I'm afraid.
Thanks.
Yet, hopefully yet, just.
More questions? Žiga, last. Oh, go ahead.
Sorry. I have a question about the cycle B in the torus. That cycle produces, in the persistence diagram, it produces diagrams that correspond to the diagrams of the circle, right? I was reading your last paper on contractions, and it says that the cycle B doesn't have a nice geodesically convex neighborhood that you referred to in a previous paper, and it doesn't seem like there's a contraction from the whole torus onto B. So I'm wondering if you have an explanation as to why there are barcodes that correspond to a cycle of length B.
I mean, I think there's a contraction from the whole space onto B. That's what I'm thinking about. Maybe I should look at it. But in terms of neighborhood, I think the neighborhood should be of length maybe 2/3 of the length of B, something like that. And here B is really long with respect to this thing. So a neighborhood like this would be fine, but it's kind of not big enough for the geometric, yeah, for this local condition. So you would want kind of this length to be, if this is alpha, I'm guessing, but I think it's something like 2 alpha divided by 3 or something. And it just felt that at that time that this is not enough, that, you know, 2 twice the length of beta divided by 3 is just not as big as this one.
I see. Okay, thank you.
Yeah, thanks.
More questions?
Yeah, I just have a quick question. That conjecture, what was it, Haussmann?
Yeah.
I mean, there's this classical example of just take the Hopf vibration and shrink the fibers. I mean, that gets you something, those 3 spheres approximate the base of the Hopf vibration, which is 2 spheres. Was that Ferry and Oken's?
No, no, but that's how it got. So Ferry and Open state that if you have a surjective map with nice fibers, and I forgot what nice means in this case, then you can have this sort of proximity result. So in this case, just as you said, I just took, just take the Hopf vibration and you get this thing.
Right, okay.
Actually, this step here means take result of Ferry and Okun, take Hopf vibration, oops,
Okay.
and you get this thing. So the result of Ferry and Okun is a bit more general.
I see. Okay.
Yeah, but that's a good observation here. That's actually where it comes from.
So thanks so much, Žiga. Let's end the recorded portion here.